Thank you. Amen. Thank you. I don't usually wear t-shirts when I teach, but sometimes I will wear a math t-shirt. So my wife and kids have a tradition of buying me one every Christmas. So see if you guys can get this one. So, okay. Homework's over here. So the exam starts tomorrow. It goes through Monday. Testing center closes early on Monday, so don't get stuck there. Or don't get kicked out before you have time. We don't cover section 3.4. We go right to 3.5, okay? It's a long, big section. It's on subspaces. And so we take 3 days to cover it. I don't have the reading notes up yet, but they will be up soon to help you know how far to read for that first section. So on Monday, we're starting 3.5. Okay, any questions? Okay. Looks like I forgot to erase the board. So I have a few things I want to do, and then I'll turn it over to you guys for questions. And what questions you don't have, I have things that we can be talking through and working on, okay? First thing I want to do is pray that this works. Okay, can't tell if it's still loading or not. Okay, so there's a problem in robotics as well as animation. If you're controlling something like an arm, or you want something like an arm to move, it's programmed so you can move the angles, right? You can tell what angle each joint can go to. But it's a hard problem mathematically to know what angle should each joint be if you want the end of your arm to be at a certain point. You know the point where it should be, and you know the starting position, but which angle you don't know automatically. It's hard. Usually you can't figure it out. Often there's infinitely many ways to do it, to figure out which angle you put each of the joints to get the end of your arm or the finger or the leg or whatever it is at the point you want it. And one way to do this problem, this is called inverse kinematics. I have a simple arm here. So from the origin out to A is the first segment. You can think about that like from the shoulder to the elbow. And then this blue segment is like the elbow to the end of the hand. So we just have two here. And I'm trying to get it on this red dot down there. But I only have two angles. I have the red angle here, so I can rotate that whole thing around the origin. And I also have this blue angle that I can adjust. And I'm trying to get B from there down to the goal. Now, think for a second, if I start to change the red angle, if I start to increase the red angle, which direction is B going to move? Think about that for a second. You can talk to your neighbor, tell them what you think. So if I increase the red angle, then so A is going to be kind of going down to your left. Which direction is B going to move? So talk to your neighbor quickly. And while you're doing that, if you increase the blue angle, which direction is B going to move? Okay, so of course if we increase either angle a lot, B is going to start making an arc, right? But right at the beginning, we can just think about the direction it's starting to go. It's kind of the derivative idea, right? It's going to start moving in a certain direction. Those directions are right there. So I don't know if that's what you guys thought about. You may have got the reverse directions if you thought about if increasing the angle was this way. But if this red part gets bigger, this goes down, and B will start to move in that direction. And then as A gets larger, if that increases, B will move up that direction. Now, of course, it won't stay that way, right? It's going to start making an arc in either of those. But at the beginning, those are the directions that it moves. It'll kind of stay on that path or close to that path for a little bit. Now, the question is, how do I use that to try to get to the goal? Any ideas? Well, the idea is, hey, I'm not going to try to get to the goal all at once. I'm just going to try to get closer to the goal. So this light vector you can barely see that goes from B down to the goal. The question is, how can I make that vector with these two vectors? Right? So this is exactly the peanut butter and bread problem. But instead of how much peanut butter and how much bread do I need to get to a certain dietary goal, this is how much do I scale U, so how much of the U vector do I need, and how much of the V vector do I need to get to this goal. And of course, the peanut butter bread problem is exactly a system of equations or a matrix product problem. Right? Then AX equals B, where in this case, this is the goal. We're trying to get to the goal vector point. Actually, technically, this is B minus goal. Goal minus B. This is the goal minus B vector that we're trying to get to. And A is a vector of, it's the U and V. It's a matrix made with the U and V vectors there. And the question is, well, how much of each of these do I need? How much of this do I need to get this vector? So exactly the same, okay? So think, in your mind, think about how much of U and about how much of V do you need to get to make that light purple one, or to make a path to get to goal. Just see if you can figure that out. Just approximately, like about how much of each do you think you'll need? You can talk to your neighbor while you work this out. Okay, someone got a guess? We're just checking intuition here. This is just practice. We're trying to figure out, if you can think about how to add vectors to get to a certain point. So, anyone got a guess? Yes. Okay, he said about 3V and about 1.5U. Okay, so 3V would put me from here, it would put me about up here. So I think what you mean is negative 3V. So we need to go negative 3V, so 1, 2, 3-ish. And now if I can go parallel to U, and I need much more than 1, it looks like maybe 1.5 or 2. Nice, okay? It doesn't matter what order you do this in. I could do the 1.5 or 2 first, and then I can go I can get to a point where I can go parallel to V and then do my -3. Okay. Okay, so there's the path. One of the paths. You can draw it in different ways. Okay, so this is the particular problem that we have. Is one of these is the u vector, one of these is the v vector. I need to multiply it by an x, by an xy, and figure out how to make that blue vector. That blue vector, look, it changes almost nothing in the x direction, right? Look how small, it's 0.4, okay? And it's going a little to our left because it's negative. Changes a lot in the y direction, 10, -10. So you can see it goes from about a -3 to a -7. See, so that's that vector. And I've got this system of equations here, or this ax equals b kind of system. So what's the easiest way to solve this? Or what's an easy way to solve this? So you can do Gauss-Jordan elimination, right? Or, yeah, you can do that. Since it's a 2 by 2, there's a really slick way. We can calculate the inverse. There's a nice formula for calculating the inverse. Then you just have to multiply this left side by the inverse. And that's what I've done over here. So 0.8 and a -2.15, that's the answer that I got for this. So you got the negative, so we guessed -3, so pretty close. And then we guessed more than 1 u, but it wasn't quite up to 1 u. Okay? All right, well, what do you do with that? Well, this tells you, let me see if I can move this over here now. This 0.8 and -2.15 tells you how much you should change each angle. You just have to change each angle so in those proportions. So you might pick 8 degrees and a -21 degrees to change those. So let's do that. There. So I changed those a little using those. And did I get closer to the goal? I did. And now you can do the whole thing over again. So a couple things to notice is the direction you move here, these angles are perpendicular to other vectors. That orthogonal thing comes up all the time. We're going to have a whole chapter working on orthogonality later on, but it just comes up all the time. You've got vectors, and you're often caring about the direction that's perpendicular to those vectors. Same with the arm. I know I can think about this vector, right? And as I start moving, that tip is moving in the vector that's perpendicular to my current arm position. So, and then you just keep doing this. Oops, I didn't mean to do that, but. So, oh, this will be fun. Let me hide some things here. Okay, so I do the calculation, and then I move a little bit, then I move a little bit more, then I move a little bit more. And each time, you can see like B almost follows exactly the direction of that light blue angle. So it doesn't follow it exactly. You can see the path's a little bit curved. So you're going to get another one. And the movement even looks pretty natural. It does slow down at the end. But anyway, I thought this was a really cool application, and also it uses just some of the stuff we've been working on. Like, it's not that hard. Every single step is something that you guys would understand. So if we had time to go through it and all the details. Okay. Okay, this is the second thing I'm going to ask you, and before I turn it over to you guys. So, talk to your neighbors. You're given a 4x3 matrix. Are the columns always linearly dependent? And you're given a 3x4 matrix. Are the columns always linearly independent? And how would you know? So think about those for a minute and talk to your neighbor. All right. Okay, we'll do a little survey. We're just using thumbs. So thumbs up if you say, we're just going to do the first one right now. So it'll be a thumbs up if you say that there's always independent. Thumbs sideways if you don't know, like, or we don't know, there's not enough information to tell. Thumbs down if they're always independent. Okay, so go ahead. Show us your thumbs on the first one. Up, sideways, down. Okay, lots of sideways and a few ups, a couple downs. Okay, a couple ups, couple downs, lots of sideways. So that's right. For the first one, here is the right answer. So why is that? Well, let's do number 2, and then we'll talk about the other ones, and then we'll talk about why. Okay, so for number 2, so a thumbs up if the columns are always linearly dependent. Sideways if we don't know, there's not enough information. Down if they're always independent. So show us your thumbs. Not as many thumbs. Okay, so I see some up, lots of ups, couple down, couple sideways. Okay, so on the second part, they are always dependent. Okay, so what's the difference here? You've got 4 of one and 3 of the other. How come they're not the same? Okay. So if you're given a 4x3 matrix, I just kind of made one up. The top 3x3 there is the same one we were working with yesterday. So we know that's invertible. If you row reduce a 4x3 matrix, so remember 4 is the number of rows. You always start the number of rows first, then 3 is the number of columns. If we row reduce, we could end up with this. We're not guaranteed, okay? We could end up with ones down the diagonal. You would with this one, because we already know that this is this 3x3 here is an invertible matrix. So no matter what I add here, so I know that these rows would span R3. I've got another R3 here, vector, so I know I could make those. I'm going to end up being able to zero those out, and I'm going to get a pivot position in each of these columns. So are these linearly dependent? I've got a row of zeros there. How am I supposed to think about this? John. What do you mean is what's the variable here? You say, John said, is it a variable that doesn't matter? What do you mean by variable? Okay, so you said, doesn't every row have a different variable, and this is one that doesn't matter? When we think of variables in systems, it's actually every column. Yeah, so every column has you can think about this as an X, Y, and Z still. So every column has one. But yeah, so there's not another variable associated with this, with the way we've been thinking about matrices and systems. So, okay, other ideas here, Christine? Okay, so Christine said, isn't that this last row, isn't it like another dimension that you don't really need? Yeah, that's a nice way of thinking about it. I mean, here we have 3 vectors in R4. They're 4-dimensional vectors, if I'm thinking about columns. And can I have in R4, can't I have 3 vectors that point in substantially different directions? Right, so each, as this vector isn't in the plane that's spanned by these two, and this vector isn't in the plane that's spanned by those two, and this vector isn't in the span that's the plane that's spanned by those two, they're going to be independent. That's okay, that can happen in R4, right? So I can have 3 independent vectors. Point 1 in some direction, 1 in another direction, as long as it's not on that same line, and then those 2 will span a plane, and then I get 1 more pointing in some other direction. As long as it doesn't go in that plane, those are independent. And I can do that in R4 or R5 or R6. I can go as far as I want down here. Okay. And I can, if I had this system and I augmented it with a, if I had a fourth vector over here, and thought about this as an equation of 4 planes, it's possible that I could have a solution. I might have no solution, but as long as I could still have a solution over here as long as that bottom one down there would end up being 0 when I row reduced. So that's okay. It would just, as long as I had a vector that was in the span of those three column vectors, then that system would row reduce, and I would row reduce to something like this, and then I would have 3 values and then a 0. Yes, in the back. That's right. So the student said, is that why it's not for sure? Yeah, yes. So it's possible I could put some other numbers in here and make it so I only had 2 pivot positions, and so then I would have a linearly dependent set, because this one could be written as a combination of these 2. So that's possible. So what's the difference with this one down here? Well, no matter what I do, if I row reduce, I'm going to have a dependence relation here. This is different. Here I'm in R3, and I have 4 vectors. So even in the best case scenario, I have the first 3 vectors might be independent, but then they've spanned the whole thing. They've spanned all of R3. So no matter what I add here is going to be in the span of these other ones. So it's going to create a dependent set. So I'm going to have a free variable in that sense. I can write this column as a combination of those other 3. I might be able to write 2 columns too, but this is the best case scenario, is at least getting the first 3. Maybe you do have 3 independent ones, but you can't get more than 3 independent ones. Okay, questions about this? Okay. Things swap if I'm not talking about columns, but I'm talking about rows. These rows can be independent. Right? There's no guarantee that I have a dependence relationship here if I'm talking about the row vectors. These rows, there's no way these could all be linearly, in the top, there's no way these could all be linearly independent if I'm talking about the row vectors, because I'm in the same situation down here as talking about the column vectors. So I have the first 3 would span the whole space, and then I'd have another one. But the first 3 could span the whole space. Okay. All right. Oh, last quick thing. So the TAs have noticed this on your homework. A lot of you aren't making a distinction between scalars and vectors. And you need to be really careful about that when we're communicating mathematics, exactly what we're talking about. So on the exam, when you're writing out work on the free response, you need to be sure to indicate your vectors somehow with a bar on the top or a bar on the bottom or an arrow on the top. It's hard to do bold when you're on there. I don't know, if you got a pencil and a pen, I guess you could put your vectors in pen, but no, don't do that. Just make sure you're indicating that your vectors are not scalars. Okay. Cambria, you had a question. Right, it would depend on what your matrix represents and like what you care about, or on an exam what they ask you about. So, yeah, we focus mainly on column vectors, and that corresponds to doing a matrix on the left and a vector on the right, like that kind of multiplication that we do a lot. So, so we mainly focus on columns, but you need to be able to think about rows too. The ideas are the same. Sorry, what? Well, we can think about either of the. We can think about any of these as a row matrix or a column matrix. We just think about. Well, am I thinking about each of these as a row with 3 items? You know, a vector with four vectors with 3 items, or am I thinking about it as 3 vectors with 4 items? So you could, when you first go to write down a matrix, you might end up writing it down either way, as a row, where you might, you can pick your rows and your columns, and you might end up writing it down as the transpose of what you really want, and you might transpose it. So, yeah. There's another question there. Oh, so yeah. So that question was, do you need some way to notate a matrix? This isn't universally accepted, but in the textbook we use, and mainly in class, we'll use capital letters as matrices. So that's enough. So if you define your matrix as a capital letter. So, and then vectors as lowercase letters with lines on them or arrows over them or whatever. And scalars as lowercase letters. So, good question. Okay, what questions do you guys have? I've taken up most of our time. So hopefully it's a good time. Yes, Caroline. Oops. So that question is, what if the question marks ended up all as zeros? So, so there's actually, the only way that could happen is if they started out as zeros at the beginning. And if they start out as zeros, then it's easy. You automatically know, it's another way of knowing that it's a that's a dependent set. So, and yeah, even if they ended up, if you see the end and hey, I've got 0, 0, 0 there, yeah, 0 of the first, 0 of the second, 0 of the third. That will get you your 0, 0, 0. So, good question. Okay, other questions? Anything from the practice exams you want to talk about? Yes, Rochelle.
Yeah, I looked at the first practice exam published, and number 12 was.
I wonder if that's the one I pulled up.
Yeah, I think
Oh, boom. Am I good or what? She's my plant. So, okay, let's look at this. So this is from the last semester's first midterm. There are 2 different kinds of multiple choice problems. Hopefully, you'll watch the video about the test. The test format, but some are mark all, and those are marked by they're marked by the spade right there. Okay, this version hadn't been finalized and put in that format yet. So So if you're on the exam and you see that spade next to the number, that means you can select multiple options. Okay, there's possibly multiple correct options. If you don't see the spade on a multiple choice, then you just pick one. It's like a traditional multiple choice. Okay, so look at these. Think about all of these. Figure out which ones are true and why or why not. Okay, so you can work together on this. Okay, take a couple more minutes. Okay, you have about 30 more seconds. All right, let's come together. Good job. So these kinds of problems tend to be the hardest ones on the exam. Okay? There's not a straightforward procedure for you to work through that you've been practicing, right? It's not a test of, hey, is this particular matrix invertible or not? Solve this particular system of equations. This requires you to think about the ideas and the concepts, the new ideas and concepts, and your understanding about things like matrix multiplication and invertible matrices and things like that. So I would strongly encourage you to go through all of these on the exams, these practice exams. Yeah, but the first one, if you cube a matrix and you get the zero matrix, is A invertible? How about thumbs up if you say it's invertible, thumbs down if you say it's not invertible? Okay, lots of thumbs down, a few thumbs up. Hey, this is related to something we tried to prove yesterday. What did we try to prove using elementary matrices? So if A and B are invertible matrices, then what about the product AB? What about this? Is that invertible? Yes. That theorem goes both ways. If you have an invertible matrix that's a product of two other matrices, then each of those has to be invertible. So that means if we take A times A and you get 0, which is a non-invertible matrix, then at least one of these has to be non-invertible. And since they're all the same, then, well, A is non-invertible. So, okay, so here, thinking about what you know about multiplication of invertible matrices is key to helping you through here. Does A have to be the 0 matrix? No, A does not have to be the 0 matrix, okay? One of the slides from the pre-class videos, it has an example of two matrices that are non-zero, and you multiply them together and you get the 0 matrix. So if A times B equals 0, it doesn't mean, what does doesn't mean? I don't know a nice notation for it doesn't mean, but it doesn't mean that A or B is equal to 0, equal to the 0 matrix, okay? So there are non-zero matrices, and non-zero matrices you can take powers of and eventually get to the 0. And there's actually, there is a name for those. They're called nilpotent, but we don't study those in this class. Okay, all right, what about B? If A is an n by n matrix satisfying A squared equals a negative I, so the negative identity matrix, then A is invertible. Okay, if you think it's invertible, thumbs up. Think it's not invertible, thumbs down. Or could possibly not be invertible, thumbs down. So if you have no idea, just throw a thumb sideways. Okay, so lots of thumb sideways is here. Some up, some down. Okay, what if A squared equals the identity matrix? What would you say? Yeah, because then the inverse of A is A. So you've already found an inverse. Okay, so yeah, so here you can go back to the theorem we were working with yesterday. Hey, I have a product of two matrices that equal an invertible matrix. The negative of the identity matrix is still an invertible matrix. You're just multiplying by a -1. You still have pivot columns in every single pivot positions in every single column. So I have two two matrices that are multiplied together to, sorry, two matrices that are multiplied together to get an invertible matrix. So each of those matrices must be invertible. Okay, that's one way of doing that. There is another way. I remember doing this another way last semester, but it's not coming to me right now. Okay, how about C? If AX equals B, where A is an invertible 2 by 2 matrix, B is a 2 by 1 matrix, then X equals B times A to the minus 1. Okay, true, up, thumbs up, false, thumbs down. Okay, lots of thumbs down. Good job. You guys make me proud. Why thumbs down? Someone want to shout that out? Sydney? That's right. It's multiplied on the wrong side. If it was A inverse times B instead of B times A inverse, then that would be true. But right now, B, you can't even do this. This isn't even defined. So, because you have a B, which is a 2 by 1, times a 2 by 2. So this is a 2 by 1. This is a 2 by 2. I don't have the right matchups here. I'd take the first column here, I'm sorry, the first row here, match it up to the first column. There's not the same number to match up with. I have 1 here, I have 2 here. I can't do that. Okay. All right, nice. Okay, how about if A is an n by n matrix, then A squared minus I equals that. Okay. What do we think about that one? Okay, true thumbs up. How about false thumbs down? Okay. Yeah, so Philip, are you the one that said you thought it was true? Yeah, why? Okay, very nice. So if you start with this right-hand side, you can just start using rules that you know are valid, okay? And eventually you get to this I squared issue that you're talking about. But let me get to there first, okay? So I can choose to do right distributive or left distributive. Okay, so I'll distribute this way, so I get A plus I times A minus A plus I times I, so that's valid. And then I can do the right distributive, so A squared plus I times A minus A times I plus I squared. And so here's where you're talking about, hey, I know that I times I squared is going to be the same as I, right? A times the identity is A. Identity times A. So those A times A plus a negative A are going to add to 0. So I get A squared plus I. So it is, oops, did I miss a negative? I did. So don't do that on the exam. Just showing you guys what not to do. Learn from my mistakes. So, okay. Yeah, so here, this is one you can just start doing, and as long as you're using properties that are always valid, okay? So A times A, it does say it's an n by n matrix, so you know that that's defined. That would be a nice way to trick you guys up, right? Is say it's an m by n, where m doesn't equal n, or something like that. So then A times A isn't even defined, and then you might be in trouble. So, okay, someone's raising their hand. Never mind. Okay, is this helping? Yeah, we're going to get to one problem. If A is an invertible matrix, then 2A, the inverse of 2A is 2 times A inverse. Thumbs up if you say true, thumbs down if you say false. Okay, not a lot of voters here, and I see about half and half. Okay, so this is false. Yeah. So one way to see this is false. You could try an example for one. So you could pick the identity matrix, just a 2 by 2 identity matrix, and say, oops. Man, I'm really self-centered today. So 2 times A, that's going to be 2002, okay? So I'll let A equal that. And then what's the inverse of this? Well, you could do your row you could augment it with the identity matrix, or you can do the can't think today. You can do the shortcut formula. So you can swap these. So 2002 divide by the determinant, which is 4 minus 0. So 2 over 4, 2 over 4. That's going to be 1/2, 0, 0, 1/2. So this is the inverse matrix of that. And so when you have 2 times A inverse, this inverse applies to that 2 also. That's going to be 1/2 times A inverse. Okay? So there's a theorem in the reading that talks about that. Someone had their hand raised. Is it? Yeah, okay. So if you think about this as transformations, so if you did the transformation and then double that vector that you end up with, then to undo that, you've got to cut that vector in half and then do the reverse transformation. So that's another way of thinking about that. Okay? If A and B are matrices of the same size and B is invertible, then B inverse AB equals A. What do you think of this? True or false? True up, false down? Okay, I don't see 1 up. That's right. You can't, unless it tells you that they commute, you can't start changing the order of those multiples. So good job. If A and B are matrices of the same size and B is invertible, then B inverse AB squared is B inverse A squared B. How about this one? True up, false down. Some of you may not have got this far, so maybe you haven't thought about this. So this is true. Why? Because you can just start writing it down. B inverse AB squared is B inverse AB times B inverse AB. And then you can take off the parentheses because associative law, and B times B inverse is the identity. And then you have AIA. Isn't that a company? Okay, so the identity times A, or the A times the identity, is just going to get A. So you're going to end up with A squared in the middle, and you get B inverse A squared B. So just using the properties of multiplication, you can show that the left is equal to the right. So, all right, last one. If A and B are of the same size and are invertible, then A plus B is also invertible. What do we think about this? Take a minute and think about this one for, never mind, we're out of time. Okay, thumbs up if you think it's true. Thumbs down if you think it's false. Okay, this is false. So this would be a nice one to try things out. See if you could create a non-invertible matrix. So this is a nice non-invertible matrix. It's really non-invertible. Can I add 2 matrices together that are invertible and get this? Yeah, like 1, 0, 0, 1 plus a minus 1, 0, 0, minus 1. There you go. So it's not true. All right, study hard and have fun. Have fun studying hard. That's not an oxymoron. So, and if you need help finding someone for the assignment with the codes, you can email the TAs and they'll help you out. So, yep.
From 6 from the exam. And I know how to, I'm pretty sure that's how you get it into vector form. You just subtract one from the other, right? The point minus the vector. So you want to find the equation of the plane.